This is going to be a fireside chat with Jeremy. Jeremy is the CEO of RISC Zero, and we're going to talk about all the impressive things that they've been working on, especially with the launch of Boundless. So without further ado, please welcome Jeremy.
All right. Hello, everyone.
Hi. I want to jump right in because there's so many questions that I have, so I want to see if I can get through most of these. But kind of the high-level question, we'll kind of make this for the audience first, is tell us about what Boundless is and why did you decide to focus all of your efforts on this update?
Yeah, so, we were the creators of the original sort of general purpose ZKVM. But the reality is that if you want to do verifiable computing, if you want to do computing off chain using ZK, there's a lot more to it that's required than just being able to run a ZKVM, because you have this question of who's doing the proving, how is it getting verified, how is the payment processing working. And so basically Boundless is what we're calling sort of a universal ZK protocol, and the idea is to bring the power of verifiable computing to all of the existing chains, right? So we're not making a new L1, we're not making a new L2, we're actually making a new protocol that uses smart contracts on existing chains and these new cryptographic primitives to basically make it possible for people on any chain, say Ethereum, say Solana, to request execution off chain, get that execution done by a decentralized set of provers, and get the results back on chain and verified. So the idea here really is that if you look at on-chain execution, there's only so much room in a given block, and you end up in this world of scarcity where when you want to do something computationally intensive, you have to pay massive gas costs, and there's a fixed supply, right? There's only so much in a block. So as the demand for computing goes up, the supply is fixed, the prices spike. Whereas ZK fundamentally changes that. So you in the sense that as the demand goes up, more provers can come online. The cost should never be more than the physical cost of doing the computation, which is actually now cheaper than the cost of verifiable compute through consensus. So the goal of Boundless, this has become true fairly recently as we've seen major performance improvements in ZKVMs. But it still isn't fully realized because of the complexity of doing all the sort of on-chain integration. Boundless's goal is to kind of make that seamless and bring that to everyone.
That's actually awesome because I have a bunch of follow-ups there already. But maybe to kind of set the stage, can you also compare how other ZKVMs and other ZK-EVMs differ and kind of what the pros and cons or just how they contrast to each other?
Yeah, I mean, I think that we when we came to the ZK space, one of the questions we looked at was how do people actually use this in practice, and one of the problems that ZK had, in addition to performance, was also just this usability issue, right? People don't like writing circuits; it's very development intensive, and so we had this idea. Well, what if we built a ZKVM that allowed you to run ordinary Rust code inside of ZK, so that the development process was easy? And actually, now with the stuff on Boundless, you can actually run Solidity even inside, the ZKVM. And I think that we actually sort of set a new standard, right? We've seen a number of other folks follow with this idea of a RISC-V ZKVM. And so in some sense, I think by moving toward existing standards, we've also sort of moved the industry that direction and have seen a lot of other people do the similar things. And, in some sense, the ZKVM itself is commoditizing because of this, right? Which we view as actually a positive thing for the industry and certainly for users, because the technology it becomes more similar across these different systems. Yeah.
Um, how does this compare to the last version of ZKVM that you've done? And kind of in addition to these custom, I guess, runtimes, which I think you talked about, you can run Solidity code off chain. Are there any other efficiency gains and enhancements on just the runtime and performance?
Yeah, so I think one thing to note is really, in some sense, Boundless is really like solving the sort of next set of problems once you have a ZKVM. How do you do on-chain settlement? How do you buy and receive proofs? How do you do aggregation? In some sense, though, the Boundless still uses the sort of existing RISC-V ZKVM, although we are, in addition, working on new versions of the RISC-V ZKVM. I think that, and that we are, for example, announced a partnership with Irreducible to build a version that runs with that. We're working with some people on the hardware acceleration side. Um, the the short version is that the ZKVM itself continues to get more performant all the time. I think we haven't gone a quarter without at least like a 4x improvement in performance.
And that's just because people are finding different ways to make compilers faster, or other, like, what's kind of the general trend that you get this big of an improvement every quarter?
I mean, it's really a lot of it's just engineering. I mean, the truth of the matter is that there's been a lot of theoretical breakthroughs over the last couple of years, and it just takes a while to get those implemented. And there's also just a lot of room, making fast GPU code. There's lots of places for tuning, and there's just continual innovation. And I think that what's interesting is that, about 6 months ago, we had this major sort of threshold as an industry where the cost of proving something in ZK and verifying it on chain is actually just cheaper than gas cost, even for very low gas cost chains. So actually that gas cost change happened quickly for ETHL1, but now even for very low gas cost chains, it's actually just cheaper to run your computation off chain and prove it on chain. And I think that we're going to see over this next year possibly another 10x of reduction in costs, to the point where computing using ZK will become uh, just it would be
The
silly
default.
yeah, exactly, the default. We actually think that most execution in general is actually going to move to off-chain execution, and not only will we see existing protocols moving, to that model, but we'll also see new things coming about that couldn't be done otherwise, right? So, for example, EigenLayer, in part of their slashing mechanism, is using our system in part because the amount of computation they were doing was, in some cases, like a billion gas, right? Which doesn't even you can't
I think it's a little bit more than the limit, I
a
think.
little bit more than the the gas limit, and also would be completely financially infeasible, right? Now, and suddenly you open up these new capabilities where you know running something that takes a billion gas is not a big deal, right? And so we anticipate that we'll actually see more uh, verifiable execution and more complex protocols becoming possible because of this.
That's awesome. So I want to talk about how Boundless lets you run Solidity code off chain.
Mhm.
We call it Steel. Tell us about how Steel works and just exactly what's happening when somebody's trying to run an EVM contract.
Yeah, absolutely. So, with Boundless, we sort of have these core things like the mechanisms of the provers and how we do settlement, and then we have these additional things that we call extensions, and that's just something that we are building a number of extensions. We also have a lot of partners building extensions, and so Steel is sort of one of these extensions. The idea with these extensions is a way to make the process even easier, or to wrap even the rest of the things. So the way that it works with Steel is that you can basically take any contract that exists already on chain, say let's use Ethereum L1 as the example, and you can say, hey, I just want this contract executed off chain and I want to know what result it gives me. So say it's a view method. Um, you can simply request that execution, and then Steel and Boundless will do the rest of the work necessary to figure out who's going to do the proving, get the proving done, get the resulting proof potentially aggregated, verified on chain, and then once that's done, you basically effectively get a callback saying, hey, this is the result of executing this smart contract. So in some ways, it's almost like sort of like an AWS Lambda, where really you're just saying, hey, go execute this off chain and tell me what it says. And you can run arbitrary Solidity contract, and you can access all of the existing on-chain data. And so for lots of use cases where you're, for example, doing computations on data that's already on chain, it's just like a very straightforward mechanism for people to use to be able to do large computations.
Does it require the developer to change anything on how they're doing the contracts?
Nope.
So you just get to access the state of any other protocol that you're connected with?
Yes.
Okay.
Yeah,
That's
and
awesome.
specifically, there is some complexities around the fact that sort of there's an asynchronous answer, but for anything that's like a view contract, it's literally that simple.
Amazing. I think there's
Well,
another kind of thing there with Kailua, and you're kind of also making this easier with rollups. Walk us through what that is, and then I have a few other questions about some possible concerns.
yeah, absolutely. So, similarly, one of our goals, we sort of as a company have this approach of sort of, you know, we call it sort of vertically opinionated but horizontally modular, where what we want to do is we want to have an idea of some technology for each different portion of the stack and provide that, but also allow people to do their own thing too, right? So Kailua is sort of our answer to the question of how do you do a roll-up stack. Although we also, of course, very much are happy to support people using ZK to do other roll-up stacks. We have like Tycho, for example, who's working with us, or the wonderful Solve Labs. But so our view on Kalyua, we actually are supporting both ZK fault proofs, so that you could do an optimistic rollup using ZK, and that the use of ZK just massively reduces the complexity of the sort of fraud, the fraud game, so that you can make it much faster and get faster finality. And then we're also going to support validity rollups using Kailua as well. So the idea would be that you could run a full ZK validity chain using Kailua.
So this becomes the destination instead of, you're saying, interoperability with other ZK chains. Is that right?
Yeah, I mean, one could build you could directly use Kailua to build sort of a ZKL2. So yeah.
So the kind of the thing I'm curious about is, obviously, I think anybody who's trying to build something scalable would be very excited about these things, because now they can code just the way they code now in Web 2. Or even if they're Web3 only developers, you now have this, like a 99% efficiency gain on gas transactions, and just instant sort of confirmation and just a lot more simplification. But it does mean that the data and all the information except that the verification proof lives on chain, or lives off chain. It's just the proof is on chain. And you now kind of create a separate set of things you have to worry about in terms of having data availability be robust and there and accessible. How do you think about these trade-offs? How do you kind of think about, what does this mean for somebody kind of delegating trust here to the system, and what they should be thinking or not thinking about?
Yeah. So I think one of the key things that we consider in the design of Boundless is we are very much interested in very strong decentralization. And so from the very get-go, Boundless is fully decentralized and fully censorship resistant, in the sense that the sort of boundless contracts that run the marketplaces exist on the existing chains, and they inherit all of the censorship resistance and decentralization properties of the chains that they serve. So if I want to order a proof on ETHL1, I'm inheriting those properties from ETHL1. Now, to your question about data availability, with regard to what the ZK proof proves, the ZK proof proves that some computation was run correctly on some data. And it, depending upon the use case, how you verify the correctness of that data differs. So in the case of, for example, something that's being done on L1. So for example, let's say you're using a steel example, right? In the case of steel, the data that you're computing on was data that was already on ETHL1, and part of the proof contains the sort of root hash of an Ethereum block that was used to sort of see the data. And so in that regard, that proof in fact implies the availability of all the data that the proof operated over. Other use cases, for example, might be if you're doing a privacy use case, then in fact the proof is computing on data that in fact purposefully isn't on any chain, and in fact may only be known to some user. Other use cases that we're seeing are for certain rollup use cases where they want to prove a state transition function for the rollup, but they don't want to necessarily put all of the full rollup data on chain directly. They may, for example, use some other data availability provider, say Celestia, and in addition to proving that the state transition was correctly executed, we additionally can use sort of a Celestia-like client mechanism to prove that the state of Celestia does in fact hold that data, right? So I think that it does, depending upon your use case, there is some additional complexity regarding how you verify that the data is available. But the idea is that the underlying mechanism supports multiple ways to do that.
Got it. Who does the proving in this example, and how kind of is that structured?
Yeah, so the proving in Boundless is done by a fully decentralized network of provers, right? So it's an open network. Anyone can run a prover. And there's basically mechanisms by which when a proof is requested, provers can bid on being the prover that does a particular unit of work. And they also have to stake a fair amount of a bond to verify that they correctly produce the proof in a timely manner. And if they don't, they lose their bond. The end user actually gets to select sort of what level of bond is required uh, in order for a prover to lock in. Additionally, provers, if they don't want to do that, can also just race to produce the proof, and the first one to produce it can
So you're saying they
receive its
can either
uplift.
just be available to do whatever comes in or selectively prove just a couple things that they're
Yeah,
able to?
yeah, exactly. So the idea here is that we really want the proving marketplace to be fully decentralized and to allow anyone in. What's really interesting about Boundless is there's no centralized sequencer. There's not even a new consensus domain produced. Really, it consists of these marketplace contracts on all the existing chains, some cryptography, and a completely open network of proving infrastructure that's run by multiple parties. And there's no central authority. There's no machine you can turn off to stop the availability. As long as there are people who want proofs and there are provers willing to service those requests, the entire thing functions and inherits the sort of security guarantees of the chains in which the proofs are requested and verified on.
All this sounds kind of too good to be true. So maybe I'm going to press you on. There's got to be some trade-offs. What is not as anywhere from efficient to nice or easy
Well,
with this approach? Because
sure.
this is only pros here.
Yeah,
What are some of
totally.
the cons?
I mean, I think they're really the biggest, I think, additional complexity of doing off-chain execution has to do with sort of composability, atomic composability of transactions, right? So right now in the Ethereum world, because you sort of are able to lock the state of the entire system, you're able to, call from one contract to another contract to another contract by multiple parties, and if there's some sort of a failure in the process, the whole thing sort of atomically rolls back, right? So you have this, so which is, for example, that's a core capability that's required by the sort of mechanism for like flash loans, right?
Yep.
And so with ZK proving, the idea is that while a single proof can be atomic, does add this sort of asynchronicity in the sense that there's the request of the proof and then later there's the result of the proof, and between those points in time state may have changed, so when the proof comes in you have to verify that the state is still what it needs to be for updates to happen, right? So you still could do the atomic application of it, so that adds a small amount of additional complexity. Obviously there's some small latency involved in the process as well. But generally, what's interesting is that from both a latency and a cost perspective, we have this very wonderful feature that as the volume of off-chain execution goes up, the latency and costs go down, because what happens is, aggregation allows reduction of verification costs, and the more things you're aggregating at once, actually, the more cost reduction you get.
So is this verification or generation of proofs?
This is on the verification side, right?
Okay.
And because there's two pieces of two things that have to be done. Once you decide you want something proven, you have to actually generate the proof, and then you have to verify the proof on chain. What's interesting is that in terms of the volume of proving capability, this is really, I think, the key differentiating factor. And I talked to this a little bit earlier with regard to this idea of scarcity versus abundance of execution. In the ZK world, what's fascinating is there isn't a real limit to how much off-chain computing can be done. If there's a huge set of demand for proving, anyone can spin up a new node and do more proving. And so what happens is, as demand goes up and up, the cost never rises above the cost of running a ZK prover on an AWS on-demand instance. Because if it was ever more expensive to prove something than it costs to run it on AWS, there's an instant arbitrage open for anyone who wants to spin up an AWS machine, right? And in an open and permissionless system,
Marketplace, people will take advantage of that.
Exactly. And by taking advantage of it, they actually bring the cost back down, right? And so what's interesting is that we're moving to this world where the amount of execution that you can do will become effectively boundless, right? And the amount of cost that you pay for execution will be fairly reliable. Now, we actually expect the cost to be lower than the cost of AWS on demand because people want to build a data center to do this. They can get much
reserve
lower cost.
pricing for just buying more compute.
Exactly.
That's awesome. Well, so I guess my last question is, where is Boundless now in terms of what's possible now versus will be soon, and kind of a couple of years down the road, what do you believe will be possible or you would like to see more on?
Absolutely. So right now we are in the testnet phase. We have many provers and protocols working already on the network. We are moving rapidly toward mainnet, which will be sometime this year. And then in terms of the longer direction, I think we anticipate a massive growth of volume improving and just an extreme reduction in costs, right? Like we're talking with, as I mentioned earlier, people working on custom ZK hardware, and we would anticipate that the cost of ZK proving will drop lower and lower and lower, and such that we really believe not only will most existing execution move to this model, but that really whole new types of projects will become possible because the execution will no longer be a limit for really Web3 applications.
I mean, that's going to be exciting, and I can't wait to see that world. So thank you so much for taking the time, and please give him a big round of applause.